Oh, is it ready? Oh, okay. So we are working with the chemistry of carbon in chapters 22 and 23. And this time we want to add a little functionality to our alkanes. So last class we talked about the difference between saturated and unsaturated hydrocarbons. So the saturated hydrocarbons are called alkanes. But now, as soon as we introduce at least one double bond, we have an alkene. Or if we have at least one triple bond, then we're in the class of hydrocarbons called the alkynes. Now, there's another description or a class of hydrocarbon that's unsaturated, and that's the aromatic. So let's talk about alkenes, alkynes, and aromatic, like this ring structure here. Okay, so for alkenes, the simplest alkene would be a 2-carbon chain. And you know that if a carbon has a double bond and 2 singles, it's sp2 hybridized with a 120-degree bond angle. So here's a model of an alkene that's 2 carbons. Now, 2 carbons, the prefix is eth, so we would refer to this as ethene. Now, ethene, unfortunately, has a common name of ethylene. That just defies the rules that we said last time because the YL is supposed to be a branch, but I'm sorry, it has the common name ethylene. Ethylene means ethene. The ENE ending is referring to that alkene with the double bond. If this had a single bond, we call it ethane for an alkene. Okay, so we have this nice 2-carbon chain. That's the simplest ethene. And then over here, if we introduce a triple bond, the simplest alkyne, 2-carbon is eth. So we'd be tempted to call this ethyne. Ethyne for a 2-carbon with a triple bond. YNE is the triple bond. Unfortunately, there's a common name here that really makes no sense. Acetylene. Oh my goodness, it has what you would refer to as a double bond ending. Oh my gosh, but it's a triple bond. And then what is that? Nevertheless, this is the correct name. You really don't even call that ethine. You call it acetylene, like acetylene gas. All right, so, okay, simplest alkyne, simplest alkene. So what do we want to do with that? Well, let's build something here. Let's replace a hydrogen here, with a, like just a methyl group. And notice I didn't even bother putting the white balls on for hydrogen because it's just so annoying. But if we substitute and put another, now we have a 3-carbon chain, and 3-carbon is prop. So this is propene, and then we could draw it. So we could draw it this way with the H's in there, where we replace that H and put a CH3 on them. So that's, or if we could use that nice elegant shorthand notation, we could just do that. That's propene. So those two are propene. Very interesting. Okay, so let's lengthen the chain even more. How about we try something where we have, that we start with that double bond again, and so it looks like our propene, but we're gonna lengthen the chain a little bit more. And then maybe we'll even put a branch. Wow, what is that? Well, it looks like if we're gonna name this thing, we follow the rules, we find the main chain. 1, 2, 3, 4 carbons, 4 carbons. So this is a butene, Now, in this butene, this main chain, I could have put that double bond over here. So I gotta make a distinction between where I'm putting the double bond, because that would change our butene a little bit. So the double bond starts at position 1. We're going to call this a 1-butene. If the double bond started over here, I would call it a 2-butene. But right now, 1-butene. And then I have this branch here. This is a branch off my main chain, and that's a methyl branch, and it's a position 3. 3-methyl dash 1-butene. And you might be wondering, wait a minute, why didn't you number from the other end? Well, it's the double bond number that gets priority. It gets the lowest value. So when you're numbering a chain with a double bond or a triple bond, you start your lowest number to position the double or triple bond. And then all the other branches get whatever number they get. Okay, let's try one more. Let's try, we sort of start at least with our butene, but then let's add a little bit more. Let's add a fifth, a sixth, and a seventh carbon, and then let's also put a second double bond. Oh, this is so much fun. And then we'll put a branch there. Okay, so what do we name this creature? 1, 2, 3, 4, 5, 6, 7. Okay, so it is a hept for a 7. And then we know it's going to be an ene instead of an ane because we have a double bond, but we have 2 double bonds. So here's the fancy way to talk about 2 double bonds. Use a Greek prefix. We're going to need di in there. Heptene, heptadiene, heptadiene. Yep, that's what we do. That means 2 double bonds, diene. Hepta is the carbon chain. Now we got to position them 1, 6. Oops, I said 6, I was writing 7. Starting at position 1 to 2, there's one of our enes, and the second ene is 6 to 7. Heptadiene. And then we got our branch, 3-methyl dash 1 comma 6 dash heptadiene. 3-methyl 1,6-heptadiene. That's great. Wow. All right. So let's try some of these, some alkyne. We got this acetylene, which is the 2 carbon. What if we did that 2 carbon, but then we added another? Oh my goodness. That just looks so weird, doesn't it? But it's representing 1, 2, 3 carbons. So it's a prop and it's propyne. Y-N-E ending for that triple bond. And notice how I make it 180 here. Like with the double bonds, I'm zigzagging it because I'm representing this 120-degree angle. But here, it's all linear, all in a line. But if I take my propyne and then I extend it more, yeah, then I start the zigzags. Okay, so what's this? Okay, let's count the main chain. 1, 2, 3, 4, 5. So it's pent. I just have the 1 triple bond, so it's pentyne. And I position the start of the triple bond at position 1. It's a 1 pentyne. Is there any branch? I didn't put any branch on there. Yep, so 1 pentyne would be the name of that one. Okay, now let's back up a little bit and let's think about these alkenes a little bit more. And let's just make sure, yeah, that's on there. So if I go back to ethylene or ethene, and I think about what is involved in that double bond, you might recall our conversation before where we described any single bond as a sigma bond that is formed by an overlap of orbitals. Now, a carbon in this ethene, it's sp2 hybridized. So that means the single bond here is formed from overlap of the sp2 hybrid on that carbon and the sp2 hybrid on that carbon. When that overlaps, it forms a sigma bond. That's this one bond. But the second bond happens because there's an extra, a third p orbital there, a third p orbital that overlaps and creates the pi bond. So we kind of visualize it, and I have another picture here to visualize it. The p orbitals on the carbons, before they overlap, they're out above and below the plane of the rest of the molecule. So these green parts here showing the p orbitals before they actually overlap. They're close enough to overlap, so once they do, we have that pi bond above and below the plane. So big deal, makes it nice and tight and closer. But here's the thing. If you try to rotate these these carbons. Look at this model. It's really, really stiff. I can't rotate them or I'd break them. If you try to rotate, it really would, this is simulating, it would rotate and break that pi bond. You know, the pi bond is a result of p orbitals aligning properly to overlap. If this were twisted, the p orbitals couldn't overlap and you would have no pi bond. So the idea here is around a single bond, there's free rotation around a sigma bonding orbital, no problem. But around a double bond, oh, we just can't rotate. So that makes a double bond very rigid, very rigid. And then a triple bond, it's even more interesting. We have a set of 2 pi bonds. That's extremely rigid. But that's also a linear molecule, so it's less interesting to think about that spinning around because it's symmetrical all the way around. What's really interesting is this idea that, hey, if that's so rigid, it really matters where I place atoms. So I could form a new kind of isomer if I have some kind of double bond and I start putting replacements for the hydrogens, if I start substituting for these hydrogens. So I could think about like maybe just a butene here, and I'm making this a 2-butene. So I start the double bond at the second carbon. So we have 2-butene. And so I'm trying to make that here, 2-butene. And I put that in. Hopefully you can see that. And here's the thing. I can't rotate around that double bond. So the placement of it where it used to be a hydrogen, the placement of this carbon and this carbon matters. Because if I broke this bond and instead attached it over here, this would also be 2-butene, 1, 2, 3, 4. But it sure has a different shape to it, doesn't it? It's like both of these carbons are down here. And I can't twist it to get a carbon. I actually have to break a bond and reattach to get it in this more stretched out. So I've drawn them here. Here's where it's more stretched out. And this is where they're like both down here. This is also 2-butene, but they have different shapes. I better call them something different. Same collection of atoms, but these are isomers. I can't just twist this up to get that one. It's rigid here. So I got to give us some kind of distinction to these names. I'm going to call this one trans 2-butene. And the other, with my 2 carbons on the same side of this double bond, I'm going to call it cis. Cis means same, trans means across. Cis and trans geometric isomers. It's another category of isomers. And it's very interesting because, like, I have an example here where if I were to create a cis 1,2-dichloroethene, what? Ethene, that's 2 carbons. Cis, oh, that's some kind of same side. On position 1 and 2, I have a chloro. Oh, okay, chloro branch. So this is a cis 1,2-dichloroethene, and that's a very different molecule than the trans isomer. This trans isomer, in fact, is nonpolar. The chlorine being highly electronegative compared to carbon, it's pulling in this direction, the other one's pulling in that direction, and those dipoles cancel. Whereas for this one, they're both pulling that way. So there's partial negative here, partial positive here. This is a polar molecule. Same collection of atoms, but different properties. So we give them different names. We can get even more interesting example. We can think about fumaric acid and maleic acid. These are 2 acids that are part of cells, but this one is essential to the citric acid cycle of reactions in your body that help produce energy. It's a 2-carbon chain here, but then there's this group that is trans to the other group. This is fumaric acid. You really like fumaric acid. It's essential. But this one, the cis version, the same collection of isomers, same collection of atoms, these are isomers. This version is toxic to living cells, and you need special enzymes to convert maleic over to fumaric. You don't really like that one. So geometric isomers, or this internal double bond with substitution provides another opportunity for the diversity of carbon in isomers. Okay, so these isomers are different compounds with different properties, and so you have to make sure you include cis and trans as a prefix to distinguish their names. Okay. Now, we have enantiomers. If you watch the video on optical isomers for chiral carbons, that's one type of isomer. And then we have structural isomers from last class. And then kind of a subset, but a very special type of isomer are these now geometric isomers for double bonds. We don't have any geometric isomers for triple bonds. And it's also not for every double bond, only the ones that are kind of internal with substitutions for hydrogen. Okay, so last category here is we're going to talk about the unsaturated type of compound called aromatic. So this is a model of a ring. It's a 6-carbon ring, 1, 2, 3, 4, 5, 6. And you can see that I have single double, right? So this type of model kit, the way it does a double bond is, we looked at this type of model kit. It kind of does it with this piece right here. So this is ethene. But if I were to connect and make a 6-carbon ring, so it's some kind of hex, but I alternate single, double bonds, we make a very special molecule. Each carbon only has 1 hydrogen on it to complete its 4 bonds. And this formula is C6H6. And this is called a benzene ring, a very special ring. So you can see it drawn out here for benzene ring. And so you could draw it that way, or you could just kind of do it with the shorthand notation. Instead of putting in the letter C and the letter H, we leave off the H's, and then we just have these points as carbons. And then we can have the alternating single double bonds like that. But here's the thing. We could form a resonance structure for this ring. Instead of putting the double bond there, we could have moved it over. If we move over that one, we're going to have to move over the other one, and then the next one. So this, remember, resonance forms are where you just move electron pairs around to form another structure. So they're forms, but they're the same molecules. So we say that a benzene ring is actually a blend of those 2 pictures. And it's really hard to draw, but the true structure, it's an average, a blend. And so sometimes we start to think, okay, this thing is not a single or a double right there. It's kind of like a bond in half, but then so are all the others. So we start to draw something like that. And then we get tired of making dots, so we just draw like a circle in there to represent benzene. If you don't have a circle in there, then you have a cyclohexane. That doesn't have any double bonds. All right, so aromatic hydrocarbons as a class really have some sort of benzene ring involved. Benzene is the prototype. It's a cyclic hydrocarbon, and it's also planar. Look at that. Unlike cyclohexane, which has all kinds of tetrahedral centers and has some maneuverability, this thing's pretty rigid, and it's all in a plane. It has a special stability because of this resonance form idea, special stability. Alternating single and double bonds are very interesting in organic chemistry because we say there's a lot of ways electrons can spread in this kind of system. So I'm just going to draw a benzene ring, and I'm going to look at it on the side. Okay, so let's just draw like we're looking at on the side here. And then if we're looking at the side, the rest of the side is kind of coming out at us. So I'm going to make that all wedged. Here's our wedge. It's kind of looking at the side. And then the idea is there are, as each of the carbons get closer and closer together, they're p orbitals that are above and below the plane. Remember we talked about that for a double bond. We have these p orbitals above and below the plane of a double bond. Those p orbitals are close enough so that all of them overlap. It's like one big pi bond above and below benzene. And that's really cool. That's a special spreading of electrons, p electrons, in this continuous pi system. Spreading, another word for that is delocalizing. A localization is a pinpoint of electrons. Delocalization is a spreading of electrons. And so when electrons are spread above and below, wow, it lends a lot of stability and rigidity to this thing. But it also opens up a benzene ring for attack by other molecules from the top and from the bottom. So that makes it very interesting chemistry. Now, benzene alone is, not so good for you. But what people, it's really carcinogenic, but what people do is like to take these hydrogens here and substitute, put something else on it, and build larger molecules. So we could think of maybe taking and putting like two methyl groups. So we could take this structure, a benzene ring, and then maybe we'd put a methyl group there and a methyl group there. So this is a dimethyl benzene, but that may not be enough of the name here, because I could take those two methyls and I could put them in different positions, and that gives me an isomer. That's also dimethyl benzene. And then there's one other possibility, and that's putting them on these positions. It's another dimethyl benzene. So I have to give them different names. So what we do is we start to say, okay, use the numbering. This is a 1,2 dimethyl benzene. Or we give it the name ortho. These positions next to each other are ortho positions. Now this would be a 1,3 dimethyl benzene. And we call those positions meta positions. So you don't even have to say 1,3. You could just say meta, or you get so lazy, you just say M. And then this across the 1,4 positions, that's para. Ortho, meta, para. And so building off, people can make, chains, and we can put more rings. We can even talk about fused rings. Like that's a really interesting, that's naphthalene. That's like in mothballs. That's really smelly stuff. But we can make all sorts of types of molecules with this aromatic unsaturated system. All right, stay tuned for next video.